rejection, that's feedback control. So you have a desired output, which is, low taxes, everybody's rich, nobody's unhappy, everybody gets health care, whatever it is. This is a desired outcome of society. And then whenever the politicians mess up, you throw them out. And you get new guys who also mess up, but at least there's some feedback, there's some feedback in the loop. It turns out that this notion of feedback, this notion of taking the output and putting it back into the input and controlling what the input does, is at the heart of many, many biological processes as well. So if you look at the human body, we have something called homeostasis, which means that the certain things in the body are kept the same. As you're aware, your temperature more or less remains the same, about 38.6 degrees centigrade plus minus half a degree or 1 degree. So you go out, it's minus 20 degrees outside, your body remains at 38, and you go into a very hot climate, it still remains at 38. So what's happening is that you have all these control systems for measuring the actual body temperature with the desired body temperature, and then putting into place appropriate mechanisms, shivering or sweating, which are going to heat you or cool you. Okay. Same thing is true when we have certain concentrations of salt or sugar in your blood. We have control systems. These are all biological control systems. Okay. And even it's even true for things like echolocation for bats. Bats are going to try and locate some prey. Again, you get this thing. So all of these have the same structure. So let's go back to the previous, basic feedback loop. And what I'm going to do is to replace all the systems where there are transforms. And so we have over here the plant. And instead of you doing GT, I'm going to call it G of S as the transforms. And then the input to it, this is the plant. Coming into it are the disturbance, which is WS, and the actual control output, which is U of S. And this comes from the controller, which we call, now I have to remember what I call that. D, I think, is the, so to make sure. Yeah, controller is D. Okay. And the controller is getting the error input E, and the error is the difference between the, maybe I should draw it here, the reference input R of S and the feedback value B, and the feedback is coming as the output of a measurement process H, and the H is getting the output. So this is Y of S. And that's a feedback value B of S. So everything has an S in it, and just for the purpose of simplicity, I'm going to leave out the S from now on. So this is the Laplace transform of the plant that you studied earlier. So everything is now in the transform domain. And the reason is because now we can easily see that Y is sort of G times the U and so on. So this is U plus W, for example. So if you do this, we can write down some simple equations. So the first thing we see is that, well, this one is obviously U plus W. So this output Y equals G operating on U plus W. Okay, because it's linear, time invariant, the inputs are so the output is going to be the linear combination of G applied to U plus W. So we just read this GU plus GW, just multiplication. We have B equals HY. We have E equals R minus B, because you have a minus here and a plus here. And U, the D, so U equals D times R minus B. Okay. And B equals HY. So, right. So now we can start doing a little bit of math, and we find that so U equals, so U, let's see. So Y equals GU plus GW. Just expanding that. E equals R minus B equals R minus HY by just substituting for B over here. And U equals DE equals D R minus HY. And then we can finally substitute for u over here, and we get y equals g d r minus g d h y plus g w. Okay, so I'm just substituting for u as dr minus dhy, dr minus dhy, so gdr minus gdhy plus gw. That's all I've done. But here is actually where the sort of magic comes in. So y is now a function of y through the operators g, d, h, okay? G, d, and h, okay? Where h is the measurement process, d is the controller, which is completely in our control. We can make d whatever we want. G is the plant, okay? So what we're seeing is that the output is sort of think about it, sort of the previous state of the output fed back into himself. So in some sense, y depends on y, okay? Which of course is just a mathematical notion. Obviously, y doesn't depend on y, it really depends on r. So what we're going to do is we're just going to take the, simplify this by saying y times 1 plus gdh equals gdr plus gw, which implies that y equals, this is the important form, gd over 1 plus gdh r plus g over 1 minus gdh w. Okay, so this equation over here is the fundamental equation of a feedback control system in the transform domain, this one right here, and it's sort of a very important equation, so I'm going to leave it up. I'll just explain to you what's going on. So what we have is, the goal of the system is we have some reference value r, okay, and we want the output to be r. Yes? This one over here, 1 minus, is it 1 plus or 1? Oh, sorry, it is plus. Sorry, yeah. So the goal of the system is for y to be equal to r. Okay, we want the output to be the reference value, whatever the reference value is, with the appropriate kind of transformation. And so what happens is r, if you view this over here, see r is what's coming into the system. If you draw this box like this, okay, if you look at this big box over here, I want the output to be r, and it's actually y, okay? And so y depends on r using this term gd by 1 plus gdh, and what we control is d. Okay, d is really what we're able to control, and g is the plant. Okay, so when we do control in the next class, you'll see how this works out. But basically, we have some way of getting from r to y by choosing d. Okay. In addition, y is being influenced by w, by the disturbance in this fashion, g over 1 plus gdh. Okay. So that's the way to parse this equation. We have d that allows us to control the effect of the disturbance on the output, plus the same d allows us to control for how r shows up as y. Okay. Are there any questions about this over here? Okay. So in many cases, we are able to set this to be a pass-through. So we just set h equals 1. Okay, if we set h equals 1, we're just not doing anything at all. Then this is what's called a unity feedback system. So what we're saying is that the feedback is exactly the same as the output. Now, of course, this assumes that the output is kind of being measured in the right way. Remember, when the car is moving on the road, output is the car moving on the road. We can't use that. We have speedometer, right? So we're going to say that h equals 1, meaning that we are looking at the speedometer itself as the output rather than the car. Okay, so it's a little bit of imprecision over here, but it makes life much easier to do it this way. So we just view the output to be the speedometer rather than the car itself, because for all intents and purposes, these are the same thing. If the car is moving, the speedometer is moving, car slows down, speedometer slows down. So then we can view y as a speedometer rather than the car. Okay, if you do that, then we can set h equals 1. That becomes a unity feedback system, in which case we can simplify this to be just, you can take the h out of here. So it's GD by 1 plus GDR, G by 1 plus GDW as being the system over here. Okay. Okay, so this is the basic equation, and we're going to use this equation and this figure here to study what are the attributes of a control system, feedback control system. Yeah?
How about the disturbances in the feedback? Where does it consider?
So that's a measurement error. So, okay, so if you have the two kinds of things, right, in the feedback. One could be that the measurement error exists, in which case it won't be unity feedback, right? Then there'd be some offset, and we're assuming a perfect measurement system, right? Also, we're assuming that there's no delay in the feedback. It's perfect and instantaneous feedback, which is why h equals 1. So unity feedback is idealization which ignores measurement errors, measurement delays, but I'll come to that when we talk about the constraints of the system. This is sort of an ideal feedback system. Okay. Any other questions about this? Okay. So what we want to do is to use this picture here and that equation there to consider some important properties of a feedback control system, and I'm just going to write down the properties, and I'm going to leave these up over here so that you can see this. Okay, and so I'll write down the properties, we'll take a break, and then I'll come into that. So actually, I want to do this thing before I write down the properties, right? So I want to, yeah. So I want to look at these feedback system in the context of two other systems. One is an uncontrolled system, and a non-feedback control system. So this is control system, and then a control system, feedback control system. Let me just take a few minutes to go over these three things, and we can take any example. Okay, in the book I talk about using an oven, but let's just maybe we should just continue that just to make the ideas clear. So if there is a feedback system for let's say you take an oven which has a particular thermostat, so you want to bake some cookies, you set it 300 degrees Fahrenheit or centigrade, whatever, and the thermostat comes on and off, right? So in an uncontrolled system, what happens is that we don't have any control. We don't have essentially any control knob. So you turn on the oven and it's on. Okay, it keeps heating up and it turns off when you turn it off, and that's it. There's no control. So it's not very satisfactory. We have no idea what the output is going to be. The output is what it is, right? So that's an uncontrolled system. Okay. Another example for uncontrolled system is a system which has exceeded its bounds of control, right? So we have these big floods going on in Thailand, right? So the control system for them is dams, dam and regulation and so on. But if the dams are overwhelmed with the rain, you're outside the zone of control, that becomes uncontrolled. So that's why there's flooding. Okay, flooding is an example of a unbounded system. The non-feedback control is possible. Okay, there's no reason why you can't do non-feedback control. It's just that for you to do non-feedback control, it's important to have a precise model of the system. If you knew exactly what the effect is going to be of every disturbance, then all you do is you measure the disturbance and you take the corrective action because you know the equation, right? What feedback control allows you to do is to not know the form of the disturbance. To give an example of this, let us say that you know that when you open the oven door, you know, and for let's say 5 seconds to look how the things are going, it cools your temperature down by precisely 20 degrees. Okay, so opening it up gives you 20 degrees. So you don't need feedback control system to say what temperature do I have. You say the door is open and closed. Okay, I'm just going to compensate for that by turning on the element for so many seconds or so many minutes, right? So if you have perfect knowledge of the system equation, okay, all the values, G in particular, and you know exactly what G is, then you don't need feedback. You can just do and this is what's often called feed-forward control, okay? Feed-forward control is another term that people use in systems where we know the magnitude of the disturbance, we know the system equation, we can just say, okay, I'm going to compensate for it, okay? So another example of this, if you're bicycling and you see a road curve coming up, right, you start turning. You don't look for the error term between your where you are on the road and the side of the road. You know the curve is coming up. If you're driving, a curve is coming up, you start turning already because you anticipate. Okay, and that's again feed forward, because you know in advance what the disturbance is going to be like, and you just feed it forward and say, okay, I'm going to start turning now. So that's feed forward control, not feedback. In feedback, what would happen is you would continue going straight line. You'd say, oops, I'm going away from the edge of the road, I better start turning now. So when you have a feed forward, you're actually able to reduce the overall error in many cases, but we're not going to study that further. So I just want to mention this because control does not always mean feedback control. You can also do different kinds of control. And in the feedback control system, we are basically looking at the output and comparing it to the input, looking at the error. So the error term is guiding us all the time. Okay? And as you'll see, in some cases, we actually need there to be an error, otherwise we can't have control. Okay? So there's always going to be some finite amount of error, otherwise you're out of luck. Okay? That's not a very nice thing to have. And for certain classes of control systems, error must exist. Okay? And which should not be the case for these other non-feedback control systems, for example. Also in the feedback control system, you can't anticipate future occurrences, whereas in a feed forward you can. You can say, yeah, in 1 second from now, I'm going to have this happen, so I'm going to be ready for it. Feedback control can't do that, okay, because there's no error. The error is going to happen 1 second from now. Why do you want to do it now, right? Whereas in feed forward, you can't do that. You can say, okay, I'm going to have an error in a minute, in an hour, so let me be prepared. Okay. Okay, are there any questions about this over here? Okay, so I'm going to stop here for a minute and then talk about the criteria. Just write down the criteria. So, yeah.
Can a system have both feed forward and feedback control?
Sure. Yeah, you can have subcomponents having feed forward, other components having feedback, and you can actually introduce. So feed forward would look like this. Oops. Okay, so W would be measured and given to D. So D would say I have an error and I have a disturbance or anticipated disturbance, and I'm going to feed it back, feed forward. This is a feed forward loop. So that's how we would draw it in this case. But we aren't studying that. Okay, so we want to look at the stability, linearity. Let me see what I have okay. Oops, I don't want to do, let me just do it in the order. So stability, disturbance rejection. Disturbance rejection. Okay. Okay, so stability. So we've been looking at stability a few times, and what I want to do is to touch on it once more, and then finally in about 2 weeks we'll study stability properly. But for now, we want to look at the control system as being stable. Okay, so we have a system, we want the output to be non-oscillatory, and we want it to essentially, on a step input, steadily rise to some value and stay there, like we talked about earlier. And the two criteria that people use for stability, one is called BIBO, and other one is called zero input. So BIBO, or bounded input, bounded output stability, basically says that if I'm going to give over here a command which is bounded, okay, then the output should also be bounded. Okay, I shouldn't have a small input lead to a very large output. Okay, that's basically the intuitive feeling. Intuitive description of bounded input, bounded output. Now, one could argue that in any real system, outputs are going to be bounded anyway. We never have infinite energy or infinite anything anyway, right? So typically in a real, so one could say it's trivial, because no matter what your input is, your output is going to be less than the energy in the universe. Okay, that's a bound. It's a very large bound, but it's a bound, so all outputs are bounded. Therefore, this is trivial. What we're really looking for in a practical system is this notion of disproportionate response. Okay, and so that's why the homework example is about the game of Jenga, right? So how many of you played this game, Jenga? Okay, so some of you played it. So rest of you should play it. It's a lot of fun, especially if you had some beer. Okay, before, not after. But what happens in the game of Jenga is at the beginning, small inputs, which is really moving those little tiles out, don't really affect the system much. So we have a bounded input, bounded output system. As the tower gets built up higher and higher, you find that even the tiniest input results in catastrophic collapse. Now, so the answer for what I was looking for was that in the beginning of the game, it's Bibo stable. However, as we increase the height of the tower towards the end of the game, certainly the last move is not Bibo stable, because even the tiniest move can cause the whole thing to collapse. So it's not Bibo stable. And of course, if your answer is, yeah, the energy in the universe is finite, so it's Bibo stable because the output is bounded by the energy in the universe, you can still get full credit because you're at least thinking about it. But that's the meaning of bounded input, bounded output stable. Typically, we actually define the output range. So we say the output bound is the error, right? We want to have the system to be within some tolerance of the output. So we'll say, okay, if you're driving down the road and our control goal is to be at 110 kilometers an hour, then we can say that no disturbance should cause the output to vary by more than plus minus 5 kilometers per hour, right? So the output would be plus minus 5, and any input, as long as it's bounded within a certain amount, would result in the output being bounded by less than 5 kilometers an hour. That would be Bibo. Okay, that would be bounded input, bounded output stable. So then we have a pretty nice way of describing the system. We say we have feedback control, and it's stable, it's Bibo stable, as long as this disturbance here, if the magnitude of the disturbance is less than something, then the output will be obeying this particular tolerance. That would be our definition, a quantitative definition of bounded input, bounded output stable. So, any questions on that? Okay, so hopefully those of you who played Jenga, you have an intuitive understanding of what this means to be Bibo stable. All right, so we can come back to this whole notion of if you remember the bridge collapse I told you about right at the beginning when we talked about transforms. The bridge collapse was, we had an input which was the wind coming in, and the wind was coming in, you can think of it as being a steady input, a step input, okay, at a particular value. We want the bridge to not collapse. That's a reasonable definition of output stability. Okay, we want to be bounded output. And in that case, what happened was, because of the resonance phenomenon, the bridge oscillated and it fell down. So that was not Bibo stable when the particular input was bounded but had the wrong frequency component in it. Okay, that would be a case of resonant collapse. Zero input has a different connotation. For zero input, what we're saying is that we have a system and we've removed all the inputs. We don't give it any inputs. So this input has basically gone away, and you just have a self-contained system. We want to say that no matter what the initial state is, not just the zero input state, but no matter what the initial state is, eventually the output is going to become stable. The output is going to be going to the zero state. So I have some kind of state space, okay, and in the state space, and I'll precisely define state space in a little bit, not today. In the state space, we have, initially we've considered this to be zero at equilibrium, the zero state at time zero, but let's say it's not at zero state at time zero. Maybe it's very far away from the zero state at time zero. So, for example, let's take a swing. Let's say the zero state is when the swing is perpendicular. I can say that the angular displacement from the vertical is the state. Okay, that's a very simple one-dimensional state. So this is my swing. This is theta. That's going to be my state vector. It's a perfectly reasonable state vector. I want to say that no matter what the initial displacement theta is going to be, eventually I'm going to get to the zero state. Okay, that would be called, and as long as I don't keep pushing it, I'm just going to start at any value, I'm going to let it go, it's going to come down there. If that happens, then we'll call that to be zero input stable. Okay, and it's a very good property to have for a system to have. That means in the absence of any additional input into the system will eventually settle down. Okay, and it's for all possible input states. So it's a global property. This one just says that if I keep the input to be bounded, the output is going to be bounded. Okay. So these are very, very different concepts of stability. And it's important to realize the different concepts of stability, okay? And so we have to be very careful defining them. and you have to be very careful defining what is meant by the zero state. But once you do that, you can actually get a lot of power by saying, okay, my system is bibo stable or zero input stable. Okay. Any questions about this? Okay. One of the things that's interesting is that the computer networks, or at least the web server, let's look at the web server input, it's always zero input stable, because basically the input is the amount of data coming into the system. In any computer network, pretty much, if you take away the inputs, all the queues are going to drain, all the data is going to get delivered eventually, and if that happens, the system is going to be zero input stable, except, can anybody tell me where in a computer network you would not have zero input stability? Okay. So what we want is a situation where at a particular input state, we don't have dissipation, okay? Yes? It's dangerous to scratch your head in this class. Okay, so I'm going to give you a hint. Think about loops. Yeah?
Yes, if you somehow connect the output to its own input.
Correct.
Or, yes.
That's right, amplify itself. So let's think of the following situation. Let's say that you send me email and I have autoresponder responding to you, and you have autoresponder responding back to me, right? So what can happen is that if you send me mail and the right set of things happen, then we're going to get what? Oscillation, a persistent oscillation, because you send me mail saying I'm on vacation, I send you mail saying I'm on vacation, and we send each other mail back and forth telling each other we're on vacation, and it's just, and it's called a mail loop. It actually happens. It actually happens. For this very reason, in the IP packet header, we have something to prevent this from happening. What do people know what it is? Beg your pardon? TTL. So what's a TTL do?
That's a limit.
That's right. So TTL is the time to live. It's a field in the IP header. Every router that forwards the packet is going to decrement it by 1. And when it gets to 0, you drop it. Why was this put in? Because the people who designed the internet were not stupid. They wanted to have zero input stability. Okay. And so when you inject IP packets, you set a TTL. It can't be larger than 255 or 256, I guess. No, 255. And when you have that decrement, you can go at most 255 hops, and then it gets trashed. So eventually, no matter what the initial state is, the system will be zero input stable. Okay, at the IP level. Of course, in the mail level, it's not zero input stable. So for mail, we have what's called a mail loop check. So there's always a mail loop check, and that's why the mail header always carries the entire path. Okay, for those of you who've seen mail headers, you'll see that the entire path is on the header. It allows us to debug things. Also allows us to run loop checks, and whenever we find the same sender seen twice, we drop the packet. It's a mail loop. Okay, and again, why? Because we want zero input stability. So this concept of zero input stability is not just something you read in the textbook. It's because you need to have it. I mean, a designer system, think about, are loops possible? If they are, put in TTL, put in loop checks, whatever it takes, so that you get zero input stability. It's a very important property to have. Okay. Right. Any questions about this? Okay. I think I should put that in the book, actually. I forgot about putting it. It's a good thing to put, TTL and mail loop. Okay. That's one advantage of teaching. I can get ideas. Okay. Let's look at disturbance rejection. So disturbance rejection basically says I want to get rid of disturbances. So simple way of thinking about it is, let's say you're bicycling and somebody jostles the handlebar, somebody just pushes it, or you accidentally jostle it. What happens to your wheel? You go like this, and then you kind of eventually you stabilize, right? So that's the transient response. We'll talk about that in a minute. But we want to reject the disturbance. We want the disturbance to go away as if it wasn't there. And we can see it mathematically right here. So let's say that we didn't have a control system. So if we didn't have a control system, we would have the plant like so, and we'd have some reference value R, and we'd have some value W, and the output is going to be G times R plus W, right? In an uncontrolled system, the output is going to be G operating on R plus W. That's my command. That's what I want to have. This is the disturbance. And so what happens is G operates directly on, so Y is getting GW, okay? Instead, what we're going to get over here is Y is getting W divided by 1 plus GD, okay? So if the value of GD in magnitude is large, what will happen is the disturbance getting reduced, okay? So we are getting rid of the disturbance by this value over here. This is often called the loop gain. We'll talk about that later. But the intuitive notion here is that the disturbance is getting removed over time by the action of the control loop, okay? So what's happening is, if you look at it more clearly, is that in the bicycle case, you are the controller. So the handlebar gets shifted. You say, oh, I have an error because my direction is not the right direction. So you have a counterbalance, okay? And if you do it too much, you go way over, right? And if you do it response too much, then you're actually going to have unbounded oscillation, you're going to fall, okay? If you have a heavy bag on your bicycle handlebar, okay, like a shopping bag, and you get a disturbance, it'll actually oscillate uncontrollably and you'll fall down. So has anybody experienced this? Or? Okay, yeah, you have, so me too. If you have a heavy shopping bag in your bicycle, be careful because you don't get bibo stability. Okay, you get bike fall down, instability. You can try it also, just put a heavy shopping bag on your bike and kind of turn it and you'll find it becomes unstable. But at any rate, with the feedback control system, what happens is that if you have the right loop gain constant, this W is going to actually get removed by a factor of 1 plus GD. And that's what we call disturbance rejection, because your feedback error tells you something's happening and then you respond to the error. And if you do the right thing, then it's going to go away. At least it's going to be diminished. Finally, the transient response is what happens from the time that so we have some value of, let's say this is time 0, we have some stable system, and then we get a step input, and then we get some response like this, and then we get back over here. This over here is the transient response, okay? This is what happens when some disturbance hits you, okay? Bounded disturbance, let's say. What we want to do is that we want to control the shape of the output Y, and we do that by basically looking at this 1 plus GD again, okay? And by choosing D, which is our controller right here, by choosing D, we can compensate for the plant in such a way so that the disturbance and the transient response are where we want it to be. So it's bounded, it doesn't cause too much trouble, etc. And so we're going to do this by essentially looking at the Laplace transform, or the inverse Laplace transform of this, where this is now in the denominator. So we're going to get some polynomial, 1 plus GD is a polynomial in S. So we get the roots of the polynomial. And those roots, when we take the inverse Laplace, correspond to essentially exponentially decays. So the values of the roots of this polynomial, okay, are going to tell us how the system behaves in the transient. And I'm kind of waving my hands here. We'll look at it more carefully in the next class. But what happens is that by choosing the roots to be in the left-hand plane of the complex plane, we'll get the transient response to be much better. Okay, and what happens is that we can choose the roots to be such that we get a very quick decay in the transient response. But if you make a big mistake, if you do that, one possibility is you can become unstable because you're too responsive. Okay, so but you have to choose it properly. But at any rate, we do have control over the transient response because we have control over D. There's this control knob that allows you to choose the transient response. Okay, so these are 3 parameters that we want to take into account when designing a feedback control system. This control system should be stable. It should reject disturbances. This we get sort of for free, and we want to control the transient response. Be nice. Just a preview. What I'm going to do in the next class is to look at 3 more criteria, and then we look at 3 standard controllers: proportional, integral, and differential control systems, what are called PID, and that will be the topic we'll discuss next time. Okay, thank you.